I'm going to walk you through something called Lloyds Mirror with our microwave system, and this is an interference effect, so let me show you what's going on. So here I've got the microwave transmitter and I've got the plate receiver over here. I've also got one of the metal reflectors from the microwave accessory packages, and I've also set up a couple of rulers. So I've got a measurement axis along this direction and also along this direction. Now I've given both the transmitter and the receiver 9 volts. So this thing is already emitting microwaves, and then to see what we're picking up I just need to adjust the sensitivity on the receiver. So let's do that and see what happens. So this thing is collecting microwaves, and that volume is proportional to the intensity that it's receiving. So if I turn this back up now, and then if I move this reflector towards the apparatus, let's see what happens. So you should have been able to hear there that it's moving through maxima and minima, so that is the interference pattern that we're moving through. So let's move back to the whiteboard and see if we can work out what's going on. Now in interference, we know that every time it passes through a maximum, the path difference between this way and this way needs to equal a whole number of wavelengths. So if we write that as an equation, it's going to be 2L minus R, so path difference, it's going to equal a whole number of wavelengths. Now this is starting to look like something we can plot now. So we want lambda to be our gradient. We can't plot R because it's constant, so we're going to have to plot this thing as well. So if we rearrange, we will get 2L equals, I'm going to rearrange that, I'm going to write that the other way around, so lambda n plus R. And then if we compare that to the linear line equation, y equals mx plus c, we will see y equals mx plus c. So y is going to be what we plot on the y-axis, 2 lots of L. M is going to be lambda, our gradient, and on the x-axis we need to plot n. So our graph is going to look like n on there against 2L, nice straight line, and our gradient is going to be lambda. Now obviously we haven't got L, but we can work it out from x and r. So we just use Pythagoras' theorem, a squared equals b squared plus c squared, so let's do that. So we know that L squared is going to be x squared plus r over 2 squared. So it's going to be big square root so for every value of x that we've got, we then need to work out a value of L, times it by 2, and then we can do the plot. So let's do that. So that's my data grabbed. Let's have a look in more detail. So here's my data set for the Lloyds Mirror experiment with the microwave equipment. So here I've got the R value, so that's the distance between the transmitter and the receiver, and that's 30 centimetres. These are my values for the position of the reflector plate. and that's in centimetres as well. So I need to plot that against n, where n is the order of the interference fringe. So the one that was closest to the apparatus is 4.5 centimetres, that'll be n equals 1, and they go up in steps of 1 all the way down to the bottom. So now we need to turn our values of x into a value of L. And then going back to that big long equation that we wrote out on the board, L is equal to, let's do the bit in the square root first, so it's going to be R divided by 2. I should point out that I'm keeping everything in centimetres just so I don't have to change everything at the end. So it is that squared, and then big bracket around all of that, plus x squared, and a bracket around that, and then I want to square root the whole thing. SQRT. There we go. And then I want to times it by 2, so 2L is going to be that times by 2. And then I want to make sure that this grabs that cell B2 on every occasion, so I'm going to put some dollar signs in here and then drag both of these columns down. And then I want to plot 2L on my y-axis against n on the x. So I'm going to highlight these columns, go to Insert, go to Scatter Graph, and there we go. Nice. Put some axis labels on there. Get rid of that. This needs to be n, and my y-axis was 2L, and that's in centimetres. Chart title is Lloyds Mirror, and then if I apply a trend line to this, make it linear, and I want to display my equation on the chart and R value and all. Drag that somewhere sensible so we can see it. So that is giving me a gradient M of 2.7544. Nice. M is 2.7544. So we know on the top of the microwave kit that it says it's 3 centimetre microwave, so 2.75 in centimetres isn't too bad. Let's work out what our percent error is. Percent error. So we want that minus, hang on, we'll do 3, which is the actual, minus the measured, brackets around that, divide by actual, which is 3, and then times all that by 100 to get percent error, and times 100. So that is, so yeah, our value for wavelength is 2.75 plus or minus 8%, which is really quite good. So that is one way in which you can measure the microwave wavelength using the Lloyds Mirror method. Now it's quite a crude way of doing it because I've just used my ears to determine where the maxima are, but I still managed to get a really sensible value for the wavelength. There's a couple of other ways that you can determine wavelength with this apparatus, and we'll look at those in my other videos. Thanks for watching.